Hi, welcome to Exploring Light. This is week 2, the history of light, and this is our fireside chat. I'm one of your instructors, Eric Muller.
And I'll be running the events today because it's week 2 of the history of light, and I'm Paul Doherty.
And hi, I'm Zeke and I have a few matters of business to discuss for today's activities. So the first thing is that some people have been talking about how to post videos and photographs to the discussion forums. So let's start with the videos. So there's no way to directly post a video to the discussion forum. It doesn't accept the video uploads. So the easiest way is to take your video and upload it to either Vimeo or YouTube. And in YouTube in particular, you can make it a private video so that only if someone with the link can look at it. I think that's actually called non-publish. And then you can put that link into the discussion forum, and then we can click on that link and go see the video. And that's probably the easiest way to do it. Like I said, there's Vimeo and other sites you can use as well. For pictures, though, there's an icon that looks a little bit like a mountain. So like when you've been typing your text in, and there's sort of a mountain and a little sun icon, and when you click on that icon, then you can upload a photograph to it. It works less well on mobile than it does on your computer. But you can, most modern devices, you'll be able to do it, but some of the older ones, you might have a little bit of struggle. And then the last thing I want to point out is that some people have been worried that they can't find exactly the right materials that we specify here in the States, especially if you live in other parts of the world. But what a lot of people have done is come up with some very creative substitutions. And if you look around on the discussion forums, you can usually find someone who's come up with something new or different that works pretty well. So keep at it, keep trying other things, and we'll highlight some of the most interesting ones as we go through it.
Oh, thanks, Zeke. And next, in going into the history of light, I wanted to start with one of the simplest possible observations, and that is that light travels in straight lines.
Hey, you know what? Before that, can I do something from last week?
Oh yeah, oh that's right.
Yeah. So I know week 1 is over before we hop into week 2, but I actually was talking to Paul and saying, hey, the Exploratorium developed this app for iPads. It's also good for certain Samsung tablets, but I really wanted to push this because it's really popular on the Apple Store, also on the Samsung/Android store. It's a great app, and I really want to push this to you and make sure you try it. If you haven't tried it yet, get this one and do it yourself. So I'm going to switch cameras, and my iPad, let me see, right here. This is my iPad right here, and it's called Color Uncovered. It's a great app. We actually have several apps now out. We have Color Uncovered, we have Sound Uncovered, which is also a great one, and we have one called, what's it called, How Many Saturdays?
How Many Saturdays?
Yeah, if you want to find out how much longer you have to live and how many times you've, how should I put this? How many times you farted in your life and how many times you're going to fart? What else is on the other one?
How many times you get to eat ice cream on a Sunday?
Yeah. So get that one too, but the one I'm going to focus on now is Color Uncovered. I'm going to turn it on right now. And it turns out that on this app, there is many little activities you can do, but I'm going to focus on this one over here. Just to let you know, this picture over here that you're looking at, this is a picture of the old Exploratorium. This is the Exploratorium this is the building we were in, or right next to this, for the majority of our life. We are now located on the piers in San Francisco. But this is the old one, and this is a picture of the old Exploratorium. I highly recommend going here. But what I'm going to do is this is a black and white picture. I am going to start this activity. I'm going to start this activity, and when I start this activity, you can notice that it's no longer a black and white picture. It is a picture of complementary colors. So if you remember from last time, we have 3 kinds of cones. We have red, green, and blue. And you'll notice the sky is a really weird color. and these bushes over here are a really weird color. So what I'm going to do is I'm going to press this X, and I want you out there in virtual land, you are going to stare only at that X. Don't deviate your eyes. And at some point, this picture is going to flick, and I'm actually going to give you a heads up on this. It is going to flick into another image, and that image is going to be a black and white image of this. Watch what happens. You ready? You guys ready out there? Here we go. Keep an eye on that X. Don't look away from the X. Stare at the X. And remember, at some point, stare at the X. When you are staring at the X, it'll flick to that black and white image of the old Exploratorium. It will do it automatically. So, what did you see? What did you guys see, by the way?
Well, I saw it in full color with a blue sky and green bushes, but then as soon as I moved my eyes, it snapped into black and white.
Yeah, so it's interesting. Just to let you know, this upper part here, black and white, but before, this was in essence, the opposite or complementary opposite of what a blue sky would look like. And so we, in essence, did a bird in the cage experiment on this app. And it actually has a weird name. What's the name of this experiment, Paul?
The Spanish Castle Illusion.
The Spanish Castle Illusion. That's kind of an interesting name. But I highly recommend, if you get a chance, do all of the activities on that. We just showed you one. But now that we are done with that, I wanted to hop back, and I want to have Paul talk to you about this week, which is week 2, History of Light.
That's right. And I want to remind people that you can type in your questions and comments in the Q&A, under the Q&A button as you're logged in. So go ahead, and as we're going through, type in your comments and questions. We've read all of your discussions, and we're trying to respond to those today, but we will take your questions live. Oh, and someone noted that they saw, Kaylee noted that she saw full color. So
that's great.
Thank you for chiming in.
Yeah, and confirming that phenomenon, it works, and it works really well. Yeah. Get the app. Try it yourself, too.
So for today, it's the history of light. We're going to start off with the fact that light travels in straight lines, and that explains pinhole images. So Eric here is going to show us a bit about pinholes.
Yeah. So I am going to, actually, I'll talk right over here. So you had an activity that you were assigned to do called the pinhole magnifier. And the pinhole magnifier had you building a pinhole out of a piece of aluminum foil and an index card. And just to let you know, that is incredibly expensive for us because you could get even cheaper than that. So I'm going to tell you other ways to do this even cheaper than aluminum foil and index cards. So if you're at a restaurant, just to let you know, you could actually use the pins in a salt shaker. And if that's too expensive for you to go to a restaurant, any restaurant, and you do a salt shaker, you can actually just say, can I have a complimentary packet of crackers? And it turns out that a lot of crackers have these little pinholes in it. So you can use the pinholes on a cracker too. And if that's still too expensive for you, you can do this activity with your fingers. If you put your fingers together, you can make a pinhole with just your fingers. Just to let you know, if you are out somewhere and you forget your glasses and you need to read something, things become clearer and you can actually magnify it with your fingers. A cracker or a salt shaker or any kind of pin.
And I can go you one better, Eric.
What's that?
You used 4 fingers to make a pinhole. I can use 3 fingers to make a pinhole.
Oh, wow. I could use 2.
Okay.
Yeah. So
Does that what makes squinting work?
That's how
you can use none.
You use none. Okay, you beat us. Squinting.
But that's the essence of the Teacher Institute. We'll give you something that works as a snack, but you can substitute other things to make it work. And this is a great example of substituting.
Yeah. So I'm just going to really quickly go through what's going on with those pinholes. And I'm going to use use, let me get some more cups. You guys fill in. I got to go get some cups. Hold on one second.
Okay, so let's see what we got here. Yes. So Liliana indicated that yes, you can use a computer to do those experiments.
Yeah.
So, go ahead.
Yeah, you can actually look so close, you can actually see the pixels on your screen by using your fingers or by using a cracker.
Okay.
So over here, I have 2 cups. They don't look identical, but let's pretend they are. Let's pretend this is the real cup out in the world. And I got my fingers close like that. And just to kind of make this work on this screen I have here, I'm going to move my fingers like that. So here is my pinhole right over here. Here's the cup that I'm looking at. So when you look through a pinhole, you don't have to really even use your lens or your cornea. You are using the pinhole. So rays of light that come off the top of the cup will go through the pinhole. And if you notice, the only way that a ray of light from the top of the cup can go is down towards the other side over here. The other ray of light that is coming from the bottom of the cup, the only way that can get through the pinhole is if that one too crosses over and that one's going towards the top. So if you're looking at a cup, here's the top, here's the bottom. What's really interesting is that the image will be inverted, okay? And if you make your, and I'll show you another way to see this inverted image, but the quick thing is that as far as magnification goes, in this situation over here, this cup and this cup are the same size. But if you get closer, and I'm going to change cups now, and let's pretend this is the real cup right here, and this is the back of your eye over here, you can actually move in so close that you can make the image on the back of your eye get bigger. And so you can actually magnify the image on the back of your eye. Smaller cup, bigger cup. Or if you have a big cup, you can make it, depending on how you orient stuff, you can make something big, obviously, because you make a big cup in real life become small in the back of your eye, but you can change how the image appears in the back of your eye, whether it's small or big.
By the distance to the pinhole.
It's all the distance to the pinhole, and the pinhole is in front of your eye. That's exactly right. It's You could just do angles, equal angles. Okay. One more thing I wanted to talk about as far as exploratorium snacks and cheapness and improving things, because I know that Zeke was saying that he actually beat us on all the cheapness as far as snacks go over there. Let me go like this. So on your listing on week 2, we had a snack that used a box, like a box of cereal or a shoe box, and you put wax paper in it, and you cut here, and you do this and do that. And we realized that actually we have a better design. This design is going to come up a lot next week during Zeke's week. What's next week, by the way?
We're going to learn about how lenses make images.
Yeah. So we're going to learn about lenses make images, but one of the lessons next week is also on the straight line phenomenon of light, and a better version of the pinhole viewer online is on week 3. I highly recommend, if you want to try out a pinhole viewer, this is the version I would recommend. Aluminum foil on this side, pop your hole in that. This is wax paper on this side.
That's the screen.
And this is the screen. You're going to be looking at this from about 20 to 30 centimeters away. And one more thing. Is there a piece of black paper around? Oh, I got it. If you're going to look at the world through a pinhole viewer and you're going to go outside, you need to have this screen dark. So you're going to look at things. It's going to go through there. You're going to have whatever real object is going to go into there, and it's going to be projected on this side. But a lot of times when you're outdoors, it might be kind of light out there. So one of the ways to help you out is to put a piece of black paper around your viewer. You could put rubber bands around this, and you could look through here, and you could see the world upside down and inverted through this version of the pinhole viewer, which is the one I recommend doing. Okay?
So, very nice symmetry to it, too. Take a look. And, you know, there's no hole in there, Eric.
Oh, well, I didn't see much of the world. Tell you what, you're going to be doing it with a pin, a really small pin. I'm doing it with a pen. Don't do this. Kids, don't try this at home, but that's not bad.
I see the light.
And is it? It's the right side up?
It's a spherical light. I can't tell. Okay, there you go.
Yeah.
Good. So that's our pinhole viewer. And what's happening with the eyes lens when we use the pinhole? So we'll answer that question a little bit later next week when we do the ray tracing and using lenses. Today we just wanted to do the pinhole, but it turns out the eyes lens still does bend the light a little bit, but not enough to bring it into focus on the retina. You absolutely need the pinhole to bring things into focus when they're very close. The eyes lens just can't do it by itself. So we'll do a lot more of that next week. So great question though, and we have an entire series of activities to help you understand that.
You probably will notice that the pinhole magnifier doesn't magnify objects if you're not close to them. Right. It lets you get your eye much, much closer to an object and still be in focus. And so it's more magnified because you're literally closer to it.
Oh, I just wanted to bring up this.
Right.
So we had a comment from Kaylee. It says if you measure the distance to a building and then take an image of it using a pinhole viewer, then you can use similar triangles to find the height of the object. That is great. It's a great math activity. And just to let you know, where'd my viewer go? Yeah, so what she's saying is that let's say there is a building and it's very far away from you. It is maybe 20, 30, 40, 50 meters away from you. The images are going to go through this pinhole right here, and it's going to be broadcast over here. If you know this distance, you know the distance to the building, and you know the size of this, you can use similar triangles to figure out the size of the building. It's kind of amazing.
Kind of like 6th grade activities.
Yeah, or high school, or even later.
Linear proportion. Yeah, very good.
There used to be a golf viewer that did that.
Huh.
It assumed that the height of the pin, the little flag, was always the same height. And so when you looked at it through the viewer, the pin was different heights, and you knew you were different distances away from the hole.
You had time as a teacher to play golf?
No.
Okay, good. I didn't think so. All right. So thank you, Eric. That was really good. Straight lines, keeping us straight. And now we had a really some questions and ideas about refraction, about the index of refraction. And we know that that's why light bends when it goes from one medium to another. But we set the interesting challenge of making things disappear. So Zeke is our expert at making things disappear, in particular lunch. So tell us about how you make glass disappear, Zeke.
So when you put two materials, so usually we say that light bends when it goes from one material to another, but that actually only happens if the two materials have different indexes of refraction. If they have the same index of refraction, then they don't. Light doesn't bend, and you can't see it. Finding though two things that are the same index of refraction though can be challenging. So for Pyrex and for soda glass, the Pyrex is a borosilicate glass, a kind of lab glass. There are a variety of chemicals that get very close. So the easiest way to do it, the way that gets you can get it exactly right, is to take plain water and start mixing sugar into it. And as you mix more and more sugar into it, you can eventually get to the point, you might even have to heat it to get enough sugar to dissolve, but you will eventually be able to find exactly the same spot for it. But sugary water is a real bear to keep up with because it doesn't have enough sugar in it actually to keep mold from growing on it. So in a few days, if you don't refrigerate it, it will have lots of fuzzy mold on it, and that will be terrible.
Which is a different science experiment.
Which is a different science experiment and not the one for light and color. Another option is to use glycerin. Glycerin is very close to Pyrex by itself, and it requires no additions to it, except for the fact that glycerin steals water out of the air. And as it gets more water in it, its index of refraction goes down and it moves away from glass. Glycerin is also fairly pricey, and so it takes a fair bit of it. So we recommended you use vegetable oil. And there are a bunch of different kinds of vegetable oil. So when you go to the store, you're going to get slightly different indexes of fraction depending what they put in the oil. Canola oil is a little too low, and some corn oils are a little too high, and you just aren't going to know for sure exactly which vegetable oils you're going to get. In fact, the people who rate vegetable oil to like figure out what oils are in it often use the different indexes of refraction to figure out what kind of oil is there. What I usually do to make it is I take whatever vegetable oil, and then I start mixing it with different amounts of baby oil. So most vegetable oils are a little too high for Pyrex, but baby oil is a little bit lower than Pyrex. So if you start mixing in some baby oil with it, or light mineral oil if you can find it, then you can slowly lower the index of refraction down. So like we keep a jug that's already mixed up here at the Exploratorium that's been mixed together. And the good news is that the oil doesn't attract water and it doesn't spoil. And so you can keep it for a very long time, already mixed up, perfect, ready to go every time. And even if you're just doing it at home, I'd recommend using some sort of mixture like that, because then you can use it over and over again. And it's a great thing to pull tricks on your friends. If you can find heavy mineral oil and light mineral oil, they are both clear rather than the slightly yellow color that vegetable oil does. And the effect is even more impressive with completely clear material.
So Zeke, if vegetable oil comes from vegetables, baby oil comes from?
Please. It's this is, I mean, that's just not legal.
Okay, no, sorry. Eric, one of the teachers wrote in with this wonderful idea, and I think you have something here to demonstrate.
Yeah, so I think it was Nicole Lambu.
Yeah, Lambu, yeah.
Lambu wrote in. And so what you need is you need a Pyrex test tube, and you need, I actually have that mixture that Zeke made, but what's really important is you have a good quality Pyrex test tube, and when you do,
oh, Eric.
I blew it. I dropped.
Broke it.
Yeah. Hey, does anyone have any more test tubes around here?
No, this is that was our only one.
You know what? I'm gonna. Okay. So tell you what. It's broken. Okay, and there are the pieces right over there. So this might take a little bit of time, but let me grab one of those broken pieces. No, I got safety first. So I got a broken piece of test there. Be very careful if you try this at home. So what I'm going to try to do is I'm going to put this broken test tube inside this mixture over here. And just to let you know, something's growing already in there. It's kind of amazing. Yeah. It's kind of amazing. Hey, Paul, can you give me a hand with this one just to make sure it doesn't? Yeah. So in order to do this activity, remember, you need a test tube, which just grew, and you need this index matching fluid over here. But let's see what happens. Wait a second. That was actually pretty quick. I already had.
Wow, it grew?
I grew a test tube, and that was pretty quick.
Yeah, look at that.
Wow. You know what's really amazing about that? Is that not only did the test tube grow, I think it had kids.
What?
Yeah, I think this test tube had babies in it. There's another test tube right there.
Yeah. Wait a second.
And I think that one.
Oh, my word.
That test tube is having a baby. What a lovely way to say it loves me. Oh, wait a second. This one was a birth I didn't discover before. This one actually came out of there too. So let me see. I had the broken test tube turned into 1, 2, 3. It had 4 test tubes inside of there. So just to let you know, while I dribble with my oil around here, can I get that paper towel somewhere right over there? So this is an experiment that Nicole Lambu mentioned. I've done this with one, but I think the brilliant thing that she mentioned was nesting the test tubes. So all those test tubes match their index of refraction with that oil that Zeke created before. And I actually heard this from a teacher without the nesting part. I heard a teacher, he just leaves this oil, a container of oil on his desktop for weeks and weeks and weeks or even months. And once one kid breaks a test tube, he goes, oh no, we just lost a test tube. He takes the piece, he throws it into. And by the way, this oil has been sitting there for weeks and weeks and weeks, and the kids haven't noticed anything. He puts it in and he goes, oh, we're gonna have to grow another test tube. He pulls it out, and the kids have never noticed that there was a test tube sitting in that index matching fluid. Yeah. But that was a great suggestion, the nesting in there.
I want to point out one other interesting thing about these different oils, and that is that they are sometimes used to identify gems in the same way.
Yeah.
You can, like a ruby or a sapphire, one of the ways that you can identify it is you can make an oil that has the same index of refraction as the ruby or the sapphire, and then the same color as well, so red for rubies, clearish blue for sapphires, and then you can drop it into the oil, and then if it vanishes, then you know it's not there. And that's one way you can check to see what kind of gem you have without taking it out of the setting. You can just set the gem in it.
So if it were a cubic zirconia instead of...
Correct, a cubic zirconia instead of a diamond.
Yeah.
Before I got into teaching, I was a geologist, and I took classes in optical mineralogy. And that's how you identified minerals, is you actually saw how they matched. And some of the oils they used were fine and dandy, but some of the oils, for some of those minerals that had really interesting properties and optical densities, some of those oils were pretty nasty stuff, but they used oils to identify minerals too.
Yeah. And you can also cover up flaws, certain kinds of flaws in gems in the same way. If you soak a gem that has a crack in it in the oil, then you won't be able to see the crack when you look at it. If the oil can flow into that crack or that fault. So in the same way, you can have the hidden broken glass inside of the oil. You can have a hidden crack in a gem in the same way.
Okay, well, thanks. So how are we doing on questions? Oh, LOL, very good. Okay, so in the history of light, at the time of Isaac Newton thought that light was made of particles. And, but there were Christian Huygens thought that light was made of waves. And the thing that Newton thought was that when light came in from air to water, it bent into the water because its speed speeded up in the direction into the water. So here it is coming in, and it speeds up into the water and goes down. But if you do it with waves coming in, as Huygens thought, then as the wave goes in, it slows down as it hits. The first part slows down, and that bends it down. So one way to tell if light were a wave or a particle would be to measure its speed of light as it goes into water. But that experiment was very difficult to do. It's hard to measure the speed of light. Galileo tried in the 1600s, and he just didn't have any good timers. He invented the clock, but it couldn't measure the timing for the speed of light. So that wasn't done until 1850. And in 1850, it was found that the speed of light in water is slower than the speed of light in a vacuum, air. And the index of refraction for a material turns out to be the ratio of the speed of light in a vacuum to the speed of light in the material. So if water has an index of refraction of 1.33, it just means that the speed of light in a vacuum is 1.33 times the speed of light in water. And that was just a nail in the coffin that said, light is really a wave phenomena. But light was discovered to be a wave phenomena much before that. That was done in 1801 by this young, brilliant person, Thomas Young. He managed to learn enough languages that he translated the Rosetta Stone sort of in his spare time. But he also did a neat experiment, which you can do. And that experiment is called the two-slit experiment. And Feynman said, all of quantum mechanics can be understood if you understand the two-slit experiment. But then he added that, of course, no one understands the two-slit experiment. So it tells you about quantum mechanics. So one of the things we need is to make two slits, and that can be a challenge. But recently, one of our teachers wrote into me and said, you know, a lice comb, the combs you use to comb the nits from lice out of hair, has very fine teeth closely spaced. Maybe we could tape the lice comb and cover all of the slits except for two, and then put a laser through it. So we've arranged that right behind here. So let me show you how that goes. So what I've done is on this table, okay.
Hold on.
I'm going to start off by showing you what I have on this end. I have a laser, and on this laser, I have used binder clips to hold the laser. So very inexpensive. Optical mounts are extraordinarily expensive, but binder clips for optical mounts, that's more the speed of the Exploratorium. And actually, one of the binder clips squeezes the on switch for the laser and keeps it on. Double duty. And I'm shining that at this lice comb right here, which I have black tape on covering all but 2 slits. And the laser beam goes through those 2 slits, and it heads over there to a card. And there we have the card. And so as we turn off the room lights, you'll be able to see a pattern on that card. There we go. And you'll notice the laser beam is a narrow spot, but this pattern is broad and spread horizontally. That's called diffraction. And as we zoom in on this, you can see this diffraction pattern is there. You can see it's bright and dark patches alternating. Now, there's Eric pointing at the bright and dark patches alternating. That actually is the pattern of a single slit. If I had just one slit, which you could make also with the lice comb, you would see this very same pattern. But what you can't see because of the resolution of our cameras is that within the central dot, there are more dark lines. That this overall pattern of light and dark has many vertical dark lines in it. And that's the 2-slit interference pattern. Now, if I take a razor blade, I can actually use the razor blade and cover up one of those slits. So, and when that happens, the places on the screen that were dark in the middle because of interference become bright. Let me reiterate that. When I take this razor blade, and we can have the lights back on now. When I take this razor blade, which has been covering, so there's only one slit making a pattern, and I remove the razor blade from covering one of those 2 slits, dark lines appear. Oops. So the dark lines appear. So, sorry about that. So, oops. So what that means was I had one slit and there was a bright patch on the screen. I opened a second slit and dark places appeared. Light plus light equals dark. And the way to understand that is if light is a wave and you have the crest of one light wave overlapping the trough of another light wave, 2 waves can add up so that they cancel out. Light plus light equals dark. 1801, Thomas Young did this experiment. You can do this experiment with simple materials. You do need a laser and a lice comb. Now there's another way to do this. We always have multiple ways. What I have here is a microscope slide. And I painted it black. I followed the recipe known to us from the Rolling Stones, paint it black. And then I took and I scratched. In fact, you can see it lit by my shirt. There are actually 2 slits spaced close together in this screen. In this, I scratched the black enamel paint. You can also use nail polish off. And that made 2 slits. And then I can put those 2 slits into this laser beam as well, making sure the laser beam goes through both slits. And I get an interference pattern on the screen. And it's not as clean as that made by the lice comb. But you can do it. You can make it yourself. So this is a way that you can show the experiment in 1801 that showed that light was a wave. And so finally, the Englishmen who supported Newton and his particle view of light had to give up to the Frenchmen and who were claiming it was a wave. And it was all due to Thomas Young, who was an Englishman, a traitor. So that is how to do the two-slit experiment. And you must do the two-slit experiment. It makes wonderful patterns. Okay, so if you have questions or comments, go ahead and put those in. And while we're waiting for your questions, I'll show you how to explain the two-slit experiment. So now room light's back on. So this is one of the write-ups that we had you do. It's called the two-slit interference model, and we don't have a video for this one. But what I've done is I've made, and we give in the snack, I'll show you how to make these wave models. So I have a wave model here for blue light, and I have a wave model for red light. I made two of them, and Eric is showing you those. And we tell you all in detail how to make beautiful sine waves. And the interesting thing about the blue wave is that it's got a short wavelength, and the red wave has a long wavelength. And the ratios, we use cards which in the United States are 5 inches long and 7 inches long, and that's just about the right ratio from blue to red. And we also have cards that are 4 inches long, 10 centimeters, and that makes a perfect green wavelength. So just having the kids make these cards for blue and green and red light with the appropriate ratios will just cement into their brains the idea that different colors of light have different wavelengths. So what I've done next is on the floor, I put a piece of masking tape, which is going to represent the screen for the two-slit experiment. And over here, I made two slits. Now, I started out by making the two slits 2 wavelengths of blue light apart. So if we point it over here, Eric, there we go. Over here, where my hand is. Okay, there we go. And I have 2 wavelengths of blue and then 2 slits on this screen. So, and you can use any spacing you want, but I suggest you start out with 2 wavelengths of blue. We're getting some reflection in there. Maybe we have to turn off the room lights.
Yeah, okay.
And we'll turn off the room lights. We'll just use the regular lights. There we go.
There you go.
So now you can see the blue light very nicely and the slits. Oops, except it automatically.
It might be that one.
Yeah, but that's all right. So now what you do is you make a laser beam come in and illuminate the 2 slits. Now the thing about the laser beam is that the waves coming in are called in phase. They oscillate up and down together. And those in-phase laser beam lights come through the slits, and when light goes through a narrow slit, it diffracts, and it goes to all different angles. It hits the entire screen, as we saw. So what I can do is take the light through one slit, and take the light through the second slit, and they come through with exactly the same phase. They're both going down together. And bring them to the middle, to where this in the screen, halfway between the 2 slits. And if I do that, you'll find that the trough or the peak of one wave exactly matches the trough or the peak of the other. Both waves add together. Here's Eric coming on in. And there, yes, now you can see the crest matches the crest. So we call that additive interference. And so you've got to get a bright spot in the middle there. Now you have to always realize this is a still photograph of a still model of light that's moving at the speed of light. So these waves are going through and the crests match, and then the zeros match, and then the troughs match, and it matches all the time. It's 100% match. But now, if we go off to the side, if I bring my waves over to the side, an interesting thing happens. It's a further distance along this diagonal than it is along this shortcut way here. So by the time I reach this point on the screen, you can see, especially as it exposes, that the trough of one meets the crest of the other. And then the crest of one meets the trough of the other. And the result is the waves always cancel at this place. There is a large negative there. It's dark. So actually, back here where it was right in the middle, I usually put, because this is blue light, I put a blue dot, and that's where there's an interference maximum. And then over here, because it's a minimum, I make a black dot, and then I surround it with blue to remind me that that was the place where blue was at a minimum. That's a good activity to do. It raises lots of questions when you actually do it. But now, with the very same setup, the same two slits, the same screen, I can do it with red light. I can bring the red light in and see what happens. So I'll bring my red light in. It comes through the two slits, again, starting off exactly in phase. It starts off. I'll bring them both to the middle, the very same place in the middle, and we find out that when I do that, the crests match up, and we can actually see that. The troughs and the crests match up. There's going to be a bright red dot right in the middle. So both red and blue match up in the middle and make brightness. And now let's find out how far away we have to go to make it so that the red is out of phase. Well, it turns out the red wavelength is longer, and so I have to go further away to make the place where the crests and the troughs cancel on the red light. And that's going to be out here. So I put a big black dot and then surround it in red, so we know that that's where the red minimum was. So what happens is, when you have two slits that light comes through, it's always bright in the middle. You come over, and then there's a place where the blue goes away, a blue minimum, and then there's a red minimum. And then as we go out further, there'll be another blue maximum and then another red maximum further away. What happened is, if I put in a mixture of red and blue light, laser light, two different lasers, into these two slits, the red light goes to one place and the blue light goes to another. That is how diffraction gratings work. They split up light into different wavelengths by sending it to different angles. In Newton's time, we used prisms to bend light, and a prism bends blue light more than red. This pattern right here, you just saw. The red light is bent more than blue. It's the wavelength that matters when you're dealing with diffraction and interference, but it's the frequency of light that matters when you're trying to deal with prisms. So that's just a little run through about how to make a hands-on model, and it really is worth it. And I've done it in just a couple minutes. This takes an hour or more in a classroom to have the kids run through, but it's really worthwhile doing. Okay, so thanks to my helpers here running around with the lights.
Great.
We got any questions or comments on that yet? Hope so. Let's see. Oh, we got thanks for the tip with the oil mixtures. That was good. Okay, no extra questions. Yeah. Okay, so we're moving right along.
Inverse square.
Inverse square. And one of the things about light is its brightness. And we have a really simple way to measure the relative brightness of two lights. And some of you actually did that, and I was really pleased. And I was just amazed that I was using this technique to compare the brightness of an incandescent and a fluorescent light. But you, our participants, were using candles. And we don't use candles in the Exploratorium because
There's something romantic about that, by the way.
Yeah, I like that. The local fire marshal requires a $300 permit application in order to approve us to light a candle. The modern world. So we use light bulbs instead. And so I have the setup right behind me. So if you remember from the write-up, what we have is two light bulbs, and they're 1 meter. I used a meter stick because the math works out really easy. 1 meter between the centers of the light bulbs. And I can turn on these light bulbs. Oops. There we go. I can turn on the light bulbs. And then I can make an oil spot photometer. And so I take a piece of white paper, and I take some oil. Seems to be a theme on today's activities that we're using different sorts of oils. I take my finger and rub a spot of oil right in the middle of this card. Ah! Oops. Oops. I'll need a little mop up there, Eric.
So we don't slip on it?
Yeah. So what you can see here is that I have an oil spot. And that oil spot, there we go. It's a little too bright still. All right. But I'll bring it over here. Yeah. I think that maybe even these lights are just too bright to see it.
Can I see that one?
Yeah.
There's the oil spot.
Oh, there it is.
It's Paul made.
Yep. And you can see it's bright on the other side because the oil on the paper allows light from the opposite side of the paper to come through, whereas the white paper does not allow the light to come through as much from the other side. Well, when I take this oil spot and I put it close to one light bulb, well, you can't even see it here. Sorry about that.
Yeah, it's kind of blown out.
But as I looked at it, it's brighter on one side than the other. And I bring it over here, and now it's brighter there. So I have to find the spot where the two of these exactly match. Dark, light, dark, light. So the match is right about there. And this is 40 centimeters from the incandescent and 60 centimeters from the compact fluorescent. So what does that mean? The oil spot vanishes when the two brightnesses are the same. So I have to get closer to the incandescent to make it the same brightness as the compact fluorescent.
Can I just say something, Paul?
Yeah.
You know, the camera does not do justice for this activity.
Yeah.
When these brightnesses match, it's pretty spectacular, right? When it does that little matching.
When it matches, the oil spot vanishes. Yeah. So it's very easy to see that. So, but now we can compare the brightnesses. I have to be closer to the incandescent, and that means that it is dimmer than the fluorescent. So that because the brightness or the intensity of a light depends on the amount of light coming out of it, the power, and the area, the power per unit area. And if I get close, the power does not spread over a large area. And as I go far away, the power spreads over more and more area. So I just found out that this compact fluorescent light is brighter. It's putting out more light than that incandescent bulb. But that's amazing because that incandescent bulb uses 60 watts. It's a 60-watt bulb. And this compact fluorescent is actually 23 watts. So if you're using these in your house, you can get more light out of 23-watt compact fluorescent than you can from a 60-watt incandescent. And the other thing I can do is I can hold on to this one and find out that it's warm. But if I come over here to the 60-watt, I can't touch it for long. It's really hot. The energy we're putting into there, that 60 watts of energy, is going into heat, which is not providing us light. So,
Can I ask you a question, Paul?
Yeah.
It says, someone in the forum asked how to calculate sun brightness from info in the video.
yes, and that's what we're going to do. So if we have room lights on, I'll go over to the board and we'll show you how to do this. So I'll turn these off for right now. I thought that might be a question. So if we have the room lights on, I already have it set up on the board. Well, I'm going to, there you go. Okay, can you see that at all, Eric?
Yeah, actually, can we point that off just a little side because it's blowing out? Yeah, that light right there. Just turn it off on the side a little bit. Yeah, I think we're good.
Can you get it to the point where you can see it?
Yeah.
So the power of light bulb number 1 and the power of light bulb number 2 at some distance become equal. And power is the watts per meter squared, the intensity watts per meter squared. So I substitute power 1, intensity 1 over the distance from the light bulb to the grease spot. That's distance 1 squared. And on the other side, we use the brightness unknown of intensity 2 to the distance to light bulb number 2 squared. Well, I can rearrange it algebraically and have intensity 1 divided by intensity 2 is the distance 1 squared over the distance 2 squared. The distance to 1 was 40 centimeters, so I put in 4. The distance of 2 was 60 centimeters, so I put in 6. So the ratio is 4 squared over 6 squared. That's 16/36. And now I can solve the intensity of light bulb 1 was 16/36, a little less than a half of the intensity of light bulb number 2, even though it used 3 times the power. But the question was, how does this work for the sun? Well, I'm going to put in some numbers for you on the spot right here. So if we do this for the sun, intensity number 2 happens to be 200 watts. So I'm going to take out intensity number 2 and I'm going to put in 200 watts. And now I have to put in the distance to light source number 1. That's the unknown light source, that's the sun. So what's the distance to the sun? And the distance to the sun is 1.5 times 10 to the 8th, so kilometers. It's 150 million kilometers. So it's 1.5 times 10 to the 8th kilometers. That's 1.5 times 10 to the 11th. 1.5 times 10 to the 11th meters. And I'm going to have to square that. So that's the distance to the sun squared. And then we have the distance to the 200-watt light bulb, which was on the order of 10 centimeters. So that, I'm going to round it off. I know it was 8 centimeters, but I'm going to use 10 just so I can do it in my head. So that's 0.1 meters squared times 200 watts. And that gets me an estimated power of the sun of 3 times 10 to the 22nd, 10 to the 24th, 10 to the 26th watts. Now, the fact that that's good within an order of magnitude is just amazing for using a grease spot on a piece of paper and a 200-watt light bulb to measure the power of the sun. So again, this is a 12th grade activity. It's nonlinear mathematics. That's why we didn't do the mathematics for you in the snack. But since you asked, if you poke a physics professor, they'll give you all the math you can handle and more. Okay.
All right.
All right.
Light is a wave in electromagnetism.
Yeah, so back with the lights on again. Boy, we're really making our crew work today with lighting. So,
Thanks, crew.
yeah. Back again. So good old James Clerk Maxwell was doing experiments with electricity and magnetism. And he knew various equations for electricity and equations for magnetism. We know those equations. But he put them together. And when he put together his equations for electricity and his equations for magnetism, he found a wave equation that electricity and magnetism could go together to make waves. And he found out that the speed of those waves. And it just turned out that the speed that the waves traveled, of electricity and magnetism, was the speed of light. So he made this incredible jump that light was a wave in electricity and magnetism. And so not only did we know in the late 1800s that light was a wave, we knew what it was a wave in, electricity and magnetism. And that is a clue to how light can travel through a vacuum. Because if I take some tape, this is Scotch magic tape. So I'll take two pieces of Scotch magic tape and I'll put one of them right on top of the other. So I stick them together, leave a couple handles so I can pull them apart. When I pull apart Scotch magic tape, it separates electric charge. One of these tapes becomes positive and one becomes negative. So when I pull them apart, they're electrically charged. In fact, you can see they now attract each other. If I move one by, it attracts the other tape. Now, what's going on here, according to James Clerk Maxwell, is that this tape makes an electric field that spreads out through the air and would spread out in the vacuum. And that electric field pushes, actually it attracts other electric charges. So if I wiggle this one up and down, the electric field comes out wiggling. And that changing electric field can move the tape at a distance. So this is our first inkling that because electrostatic fields can cross a vacuum, they can cross air, that light, which is a wave in electricity and magnetism, can also cross the vacuum. So this was a tremendous discovery. We could actually add the mathematics of waves and find that light was a wave in electricity and magnetism. And there things stood until 1905. And in 1905, there was a very strange experiment. And this experiment was called the photoelectric effect. And I actually had you try this one at home. And I have it over here. Photoelectric effect. And what I have for the photoelectric effect is I have a zinc coated steel plate that's called galvanized here. And I have a beaker. And alas, right now today, my beaker has become charged, so I can't do this experiment for you. The beaker is just tremendously electrically charged. And I can't even discharge my plate. But that happens, and it's physics. Some things are harder than others. I'll work on this for next week and get it to work again. But what the photoelectric effect was that when ultraviolet light was shown onto this plate, and I have, oh wow, ultraviolet light.
I will just corroborate. That is like totally charged.
Totally charged
there.
Yeah.
Those
So,
things are just splaying out.
We have this ultraviolet light that if the metal plate were charged, which charges the tinsel, that's aluminized mylar, it would make it spread apart, and this would discharge it. In fact, touching it with my hand would discharge it. But you can see that the two little arms here are back close together. A little hard to see.
Mm-hmm.
But the jar is so electrically charged, they just spread right out, just coming close to it. Yeah. Okay. So I can't do this for you, but here's the result. We'll do it next week. Ultraviolet light will discharge this. Red light won't. Even the most intense red light you can put on it will not discharge it. Okay.
Yeah. No, I'm just showing.
Okay. So this is the way physics works sometimes. It doesn't.
That's right, yeah.
And electrostatics is really hard to make work. So I'll debug it, and we'll get it back next week when we continue with images with Zeke. And the week after that, we come back and continue to our
Zeke,
modern understanding of light. So come on back,
Well,
Zeke.
while he's walking, what is it? It's if it doesn't work, it's physics. If it stinks, it's chemistry. And if it wiggles, it's biology.
If it bites you, it's
if
biology.
It bites you, it's biology.
Okay. So there we go. So just to show you, it doesn't always work, even for the professors, and we have to figure it out ourselves, how to make this work next week. Bye.
See you then.
See you virtually. See you online.
Isn't that amazing how charged
Yeah, I know.
that
It
is?
was